Eric Burgess here, and today we're going to be doing some chi-squared goodness of fit testing. So let's just hop right into it. So we're going to be doing it using the formula and the chart, and we're going to be doing it using the calculator and the p-value method, since those are the methods that are taught at Citrus College. So let's dive right into it. A department store wanted to see if the distribution of t-shirt sizes followed the proportions 14% small, 22% medium, 38% large, and 26% extra large. A record of the sales of t-shirts is shown in the given table, which is this table right here. So this is the actual sales that they have, and they don't know if they match the percentages. They think they do. They're not totally sure. At the 0.025 level of significance, can it be concluded that the percentages are equal to those stated? So they want us to see, hey, does this distribution of values match this distribution of values? Now, down here, they're actual values, like 32, 53, 47. They're not percentages. And up here, these are percentages, right? Is 14% small. Well, it's 28, 14% of all these values. Like, we don't know. Not yet, because we haven't done any math yet. But that's what we're trying to figure out. So first things first, we see and we identify this problem as a goodness of fit test problem. And that is a clue to tell us to use this formula, because we have expected values and observed values. Well, we're going to compute our expected values. We don't know what those are yet, but we have our observed values. And we also want to know, for our goodness of fit test, what tail is it? Well, all goodness of fit tests use a right-tailed test. So we immediately know it is right-tailed all the time and always. So if you ever see this, just think right-tailed right away, right-tailed test. Now we need to come up with our null and alternative hypothesis and identify the claim. So our null hypothesis, H naught, that is always going to be the one that says things are equal. So up there it said, we want to know if the percentages are as stated. Percentages are equal to those stated. And so we say the percentages are as stated. They're equal. They're the same. That's what we're claiming. So and I'm going to write percentages as a percentage sign. Very fancy, I know. The percentages are as stated. Now, some teachers want you to attach this to the actual problem. So you would say the percentages of the distribution of t-shirt sales matches those shown by the data. You know, you would say something that says basically they're the same, they're equal. Now for our alternative hypothesis, H1 or HA, we would say, or I'm going to use equals just because I did that before. We would say our alternative hypothesis, well, that's that they're not as stated, that they're different. So we'd say the percentages are different. You might actually write out percentages on your actual test. That's what I would recommend. We're just saving ourselves a little space here by using the percentage sign. All right, so these are our two things. We want to see which one's the claim. Well, it says up here, can it be concluded? That's some keywords right there, that the percentages are equal to those stated. So that's their claim, and we know that because of the can it be concluded bit. This one's our claim, that they're equal. All right, cool. Now let's go ahead and do this thing. So we're going to need a couple things. We're going to need a test stat, or a p-value. And we're going to need a critical value for those that are going to be using the test stat method. We're going to be doing both. They're very easy to do. And I encourage you to do it multiple ways. It's very easy to check, and you'll be very sure that your answer is right. And I like to draw out the curve. Now, chi-squared curves are kind of funny looking things. They come up and they come down like this. They're not symmetric like normal distributions are. They're these sort of weird looking things. And we want to know, our critical value. So our shaded region is an alpha of 0.025. So we know it's right-tailed. So it's 0.025, so over here. 0.025. That is our alpha. So we want to know the value that would go here. That would be our critical value. And we also want our test stat, see if it falls in the shaded region. And it follows the same rules as the other ones. If it falls in the shaded region, we reject H naught. If it doesn't, then we fail to reject H naught. So let's go ahead and do this. Both methods, calculator and by hand, will require the expected values. And to get those, what is basically saying is we need to take all of these numbers, right? Because these numbers have been distributed into different categories. 28%, or not 28%, 28 of these has been put in small. 32 is in medium. So they've been split up into the categories. We're going to put them all back together and we're going to redistribute them according to our percentages up here. And then we're going to see if they're close enough to be able to say the percentages are basically the same. That's what we want to do. So to do that, we're going to take all these numbers and put them all back together. All these are our observed values. And so this is going to be our total over here, total. And let's just do that. So we're just going to turn our calculator on. We're going to do 28 plus 32 plus 53 plus 47. That gives us 160. So that is the total number that's being split apart into these different categories. Now, we want to make sure that we're splitting apart and we're going to distribute 100% of this, meaning we're going to split this up and put all of it back. There's going to be some here, 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 here. And we put it all together, we should get this back. And some teachers will give you percentages. They're tricky. They'll give you percentages that don't add to 100%. So you would write you can't actually do this problem because the percentages don't add to 100%. It's really easy to check. Just add the percentages. So you do 14 plus 22 plus 38. Whoops. Let's do a plus sign here. Plus 38 plus 26. And we see it's 100. So that's 100%, meaning we are going to split. If we take this and split it according to these percentages, they should be split up and we should use all of the 160. If this is not 100, raise your hand. Something's wrong with the problem, or it's a problem that's like a trick question and you can't really do it. So just be wary. I don't think your professor will do it to you, but it could happen. Maybe on a study guide or something. So, okay, we're going to take this and we say we want to split this 160 up now according to these percentages because we don't know what these are. We could figure it out backwards, but we're going to go the other way. So we're going to take 160 and we want 14% of that. And so to do that, you just multiply by its decimal. So you multiply by 0.14 because that's 14% as a decimal. And we get 22.4. So these are our expected values. So if we expected 14% of this, well, we would expect in the small category there to be 22.4. And now for 32, we would take 160, for medium. We would take 160 and we expect 22% to be medium. So we would multiply by 0.22. That's how much we expect. And that is 35.2. So they're a little different than the values that are here, but they're pretty close. So let's keep going. We've got 38% are large, so we take 160, our total amount. And if 38% are large, we would multiply by 0.38. We will get 60.8. That's how much we expect in the large. And then 26% are extra large. So we take 160 times 0.26. And we get 41.6. Now, it might seem strange that these are decimals, that there are decimals here, but we're doing some theoretical math, and so it's actually okay that we have decimals here. We're just checking something using math. In real life, we would never have 22.4 sales of a small t-shirt. That would be like a ripped up shirt or something. That would be weird. But for the theoretical math, totally okay. Now, there's a way to check this just to make sure you multiplied correctly. We have split up this 160 into each of these categories, and we verified that it's 100% of this. So if we add these values up, we should get 160. So if we take 22.4 plus 35.2 plus 60.8 plus 41.6, we get 160. So this just verifies that we did it correctly. If you don't get the total amount that you're splitting up, well, you're missing something. Or if you have more than, you multiplied by something wrong. So you want to go back and double check. But this is a really easy way to check, make sure you did it right. All right. Now here's where we kind of split up into two methods. So let's go ahead, let's do the calculator method first and draw our conclusion, and then we'll do it and we'll verify it using the formula. So we'll see everything, and there are timestamps below if you want to skip just to the method that you use. I recommend doing it all though. It's really easy and very quick to check on a test. So the calculator is going to want to see two lists. It's going to want to see your observed list and your expected list. So we're going to go to stat and go to edit to put it in our list. If your list isn't blank, go up to list 1, hit clear, and then come down, and all the values should disappear. So our first one, we're going to put observed. You don't have to, but it's much easier if you do. So we're going to put the observed first. So we're going to put 28, 32, 53, and 47. All right. And for the expected, that's 22.4, 35.2, 60.8, and 41.6. Cool. Now here, while we're here, let's go ahead and notice that our degrees of freedom, we're going to need that. So the degrees of freedom is one less than the number of categories you have. So we have small, medium, large, and extra large. That's 4 categories. So our degrees of freedom is equal to 3. 4 minus 1, that's 3. So in the calculator, there is a statistical test we can run, a goodness of fit test. So we're going to go to stat. We're going to go to tests. Now it's at letter D. So I'm going to push up because it's a bit quicker, but you can push down until you get to D. And we see a chi-squared goodness of fit test. So this is perfect, exactly what we want. So we're going to click that. And our observed are already in list 1, our expected are in list 2. If you put it in some other list, you're going to have to change these. Our degrees of freedom, well, that is going to be 3, like we talked about. And I want to draw it first just so you can see it visually, and then I'll use calculate. So if we draw it, it's going to actually shade it for us and everything. So there's the P value here. So we see that P is 0.335. So we're going to write that down. P is equal to 0.335. Our alpha, though, if you recall, was 0.025. So alpha was way down here at 0.025. This is 0.3, 0.3 is bigger than 0, so this is going to win. But it's way down here. So we are very inside of the safe region. We're way out here. We're nowhere near this critical value. So we could say that P is greater than alpha. Therefore, we do not reject H naught, the null hypothesis. Or some teachers will say fail to reject the null hypothesis. We don't reject it because the null is over here, right? And our critical values back here. This is where we would reject. Well, we are well within the safe area, so we don't reject. Do not reject. And that's going to say things for our claim. But that's one way to tell. There's another way. Our chi-squared value. So chi-squared, this is actually our test stat. It tells us right there. So if we write our chi-squared test stat, that's going to be 3.3925. When we're going to check this by hand, we're going to calculate this as well. And so we could say, well, this is 3.3925. That's somewhere over here-ish. It's actually going to correspond to our 0.335. So we have 3.3925. So when we find our critical value, I guarantee you it's going to be bigger than this. And so because it's bigger, we've landed in this area that's not shaded. And so we would say, again, we don't reject the null hypothesis. And so that's how you would do it using the calculator. Now, if you come in and you go to tests and you just go straight to calculate, and so instead of drawing, you said, oh, I want to calculate it. Well, here you see we get the same values. You get a P and a chi-squared value, but they're not as nicely shown because, it's not shaded and stuff. So, but you can get the exact same information and draw the exact same conclusions. Okay, so our conclusion here would be we don't reject the null hypothesis. Well, the null hypothesis was our claim. And so since the null hypothesis was our claim, we would say there is evidence to support our the claim. There is evidence to support the claim. I have made a mistake here on our conclusion. So I said there's enough evidence to support the claim, but I forgot that actually when the claim is H naught, you're always trying to basically reject it. Kind of like how if someone is on trial, you find them not guilty. You don't find them innocent. So here instead we would actually say that we did not produce enough evidence to find the claim wrong, to find them guilty is kind of what we're doing here. So we would say there is not enough evidence, is not enough evidence to reject H naught. Basically saying, if this guy, pretend the claim's a person and that they're innocent. The more and more evidence you produce, if they're innocent, then they have nothing to worry about. No amount of evidence will ever find them guilty. And so there's not enough evidence to reject H naught, to find it guilty. It'll never be proven guilty. You can only find it not guilty. And so here, we'd say there's not enough evidence to reject H naught. That's the proper conclusion. So, okay, let's go ahead and let's do this by hand now. Now, by hand, we'll need to find the critical value. And to do that, you have to use the chart. And so, to use the chart, we're just going to go ahead and note our degree of freedom is 3 and our alpha is 0.025. So, let's go to the chart. You'll need a chi-squared chart. Now, this is the one I'm using. You may have a slightly different looking one, but they work on the same principle. I'm going to look for our degrees of freedom, which is 3, and our chi-squared, which is 0.025, which is right there. And I'm simply going to just, go ahead and shade across. And where they cross, that is our critical value. Because it's determined by our area, right? And so there's the area. So our critical value is 9.35. So we'd come in here, our critical value is 9.35. That is the critical value. And we see that this is much greater than the test stat that we have. So it's just like I said, we would draw the exact same conclusion. So there's a way to check it using the table, if you use the table. Some classes do a mix of calculator and table. Let's go ahead and compute this using the formula, because again, that's another thing that way to show your work. So up here, let's take a look at this formula. So this formula says to sum, meaning to do this thing over and over and over, and then add all the parts. That's going to give us our chi-squared value. And it's really easy. We simply take the observed minus the expected. We square it, and then we divide by the expected. So let's go ahead. Let's do that. And let's do it zoomed out here. So, okay. So first off, we're looking for our chi-squared. So chi-squared will be equal to a bunch of additions of this process over and over and over. So our first one is our observed, which is going to be 28 minus our expected, which is 22.4. Then we're going to divide by 22.4 because that's our expected. And we're going to square the top, right? That's our first one. Then we're going to add the next one. So that's going to be 32 minus 35.2. That's our expected, our observed, and we're subtracting them. We're going to square it, and then we're going to divide by 35.2. Then we're going to add to that 53. This adding is what that sigma is, that big sum, that big looking E. That's what it says to do. So we're doing this process over and over and then adding them. So we have 53 minus 60.8, and then we're going to divide by 60.8, and we're going to square the top. And then our last one is 47 minus 41.6 squared divided by 41.6. Okay, so this is what we're going to do. The calculator did this for us, and I'm zoomed out so my writing isn't as spectacular. Not that it's spectacular anyways, but it's extra bad now. So let's go ahead, let's do this. We can actually enter this all in one shot in the calculator. So if we go ahead and turn the calculator on, and I'm going to clear it just so we have a clean space. We have a fraction, so I'm going to hit alpha and then the F1 key. It's up here, F1 in green. That's why we hit the green key. We're going to use a fraction, and I'm going to put parenthesis 28 minus 22.4, close parenthesis, square it. Important that the square goes after the closed parenthesis. Otherwise, you're squaring the 22.4 and not the subtracted result of this thing here. So very important you put it in exactly as the formula says. And we have 22.4 on the bottom. Okay, we're going to do plus. We want another fraction, so green key F1. We take the first one, we do a fraction, 32 minus 35.2. Then we're going to square this. And then we're going to divide by 35.2. And then we're going to add, that's the sigma thing. And then we're going to do alpha F1, parenthesis, 53 minus 60.8, close, square, 60.8. And then we're going to do add alpha F1, fraction, parenthesis, 47 minus 41.6, close parenthesis, square, come down, 41.6. Now we're going to simply press enter because that's everything. And we get 3.392528, da 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 da. Look at that. The exact same thing. So we would say all the same stuff. That's how you would do it by hand using you were using a calculator to do the calculations. But this is the big long formula you would write out. So if you have any questions about this, let me know. If you're a Citrus College student, definitely go online to online tutoring. We're there to help you out. Subscribe, and we'll see you in the next problem.